This time it didn't ask me for my password. I swear. I don't know what the hell's going on. Hi, Jennifer and Anai. I see you. Let's see. I don't know where the rest of we are. There we go.
Okay.
Where's my? Oh, there it is. My waiting room. Yes. Yes. Stephanie. Haley. Katie. Stephanie. Admit all. All right. All right. I got Anai, Tori. I got more to come here. Let's see.
Hello.
Hi. Hi, Katie. I got you up first somehow. Okay. All right. So.
Good morning.
Good morning. You're in the same place you were Friday night, sitting in the kitchen.
Yes, in the kitchen.
But I'm sitting out in the hall outside the kitchen. Okay, let's see. Let's get a gallery here. All right, I got, let me, guys, I'm gonna, we got a new assignment sheet online, so I'm gonna show everybody that so we know sort of what's coming up. And while we're waiting for everybody to come in, because it's right now 11, so I'm expecting people to come in. There's Tori with her beautiful golden retriever. And let's see what else we got. All right. Let me share the screen and show you what I've got. Take a breather while everybody else is coming in. Why do you mean sharing is paused? I don't want it paused. I just want us to go. All right. Not sure why it did that. It's, for some reason, it's pausing my share, but I don't know why. Move to the bottom, move to the top. Resume share. Let's try that. Okay. Did it, guys, did it ask you for your password today?
Yeah.
Okay. It asked me, actually asked me for mine for it, and I'm like, I thought I usually came up with my own password, but I had to go scrambling to find it through an email from you guys. So let's see what I've got here. And iTunes can't read the okay, there we go. I don't care about iTunes right now. All right, let's admit who's waiting. Who's waiting? Lainey's waiting. So got her in, I hope. And okay, so it looks like the screen is shared. I'll admit people as they come in, hopefully. And try one more time, make sure I've got everybody in. 1, 2, 3, 4, 5, 6, 7, 8, and 9 makes me. That's right. Okay, so guys, let me show you what we've got coming up, and quizzes due and so forth and so on. If I look at this thing right here, this is on Moodle. I've already put it on Moodle. It's our assignment sheet. I backed it up to last Thursday so we knew what we were doing last Thursday, because what we're doing today is some more of that. All right, we're continuing section 3.3, and then we're starting to do some curve sketching. We've done a little of this curve sketching already, so you won't find it extremely new, but we'll do a lot of examples so everybody can see what we're doing. Okay, got a couple more waiting to come in. Let's see, let's admit Shell. Okay, I think she's in. So on tonight's homework in particular, there are a few problems left over from page 194 that have to do with concavity. today I'm going to add all the concavity, the increasing, decreasing, local maxes, local mins, inflection points. I'm going to add all of that together and try to do some graphs based on those things. And so what part of the homework is, there's a few of them that are listed right here on page 233, 1, 3, 5, and 17. And I gave you a hint on how to do one of them. The other ones, I made some up myself. I know how these things come out, and I'll have a key for you for these things. But those, and this is what we'll be doing on all of these things we're getting ready to do today. So watch sort of carefully the way I follow through a problem. It says find for each of the following, find all critical numbers, intervals on which it's increasing, decreasing, local maxes and mins, including absolute maxes and mins where asked, intervals on which it's concave up, concave down, inflection points, find the domain, graph each one, labeling the points you found. So it's this whole big package of things we've been learning about that the derivative and the second derivative tell you. We'll look at a whole lot of those. Now, remember that and this happened on one of our quizzes already, when you're asked for absolute maxes and absolute mins, you have to test the endpoints. I mean, sometimes you can have an absolute max or min without having endpoints, but you're going to be guaranteed an absolute max and a min on that. And one of the things that happened in the homework was that you can have a high value, a maximum value occurring at a local, or you can have it occurring at an endpoint. What I would suggest is you do what I'm getting ready to practice today, is sort of draw the graph out, sketch the graph out, say the high value is this, it occurs here and here. Now to do that, you got to remember that when you talk about the maximum value, you're looking at the Y value or the minimum value. Look at the Y value. Where it occurs is the X value. So you can have one high value that occurs at a couple of different places. We'll see that again today. The next thing, just rough, sort of going over this thing, just see what's ahead. We're going to be doing graphs with asymptotes. I've got to talk to you a little bit about asymptotes. That'll be tomorrow. And then we'll go back to more sketching with graphs that have asymptotes. There will be a quiz due Thursday by class time. It'll be sketching graphs. It is on Moodle already. So if you want to look at it sort of to see what you need to be preparing for, it's there, okay? It'll be due Thursday by class time. Finally, on Thursday, we're gonna finish all the sketching techniques. I'm gonna give you some with asymptotes, all right? Or no, actually what I'm doing on this is I'm giving you the function and its derivatives. In other words, you don't have to take the time to find the derivatives, but you do need to take the time to tell me what the derivatives are telling you. We'll do one like that in class too, okay? So there were a couple of those on there. That sort of saves time, saves you the time of taking the derivatives, and make sure you don't make any error in the derivatives, because as you know, with some of these things, if you make an error in the derivative, everything after that's going to be wrong. You're going to find the wrong critical numbers. You're going to find the wrong increasing, decreasing, so forth and so on. So you got to be careful with the derivative. So you're fortunate when I give it to you, okay? And if I made a mistake, it's on me. The next thing we'll do after that, starting the beginning of next week, is what we call optimization problems, which are problems where we're trying to find out how we maximize or minimize something. Now, we've already done that in a business context by maximizing profits and minimizing costs. So the quiz that was due today was on that. So if you have not gotten the quiz to me on yet on profit applications or business applications, make sure you get that to me today. It's really hard for me to go back and grade piecemeal. I like to have them all at one time. So I've been trying to be a little bit lenient on it. If I see people that have made an initial mistake that's going to mess up everything, I'll send the homework back and let you look at it again. But I can't do that if it's late. I've got to have it when I want it, and then I can give you the opportunity to look at it again and hand it to me back really quickly. So anyway, that's where we're going there. We'll spend 2 days on optimization problems. Wednesday of next week, we'll review for the test, and on Thursday, we will have the next test, okay? Clearly, it's gonna be on a lot of graphing stuff and business applications, and some of this last stuff is similar to business applications. You're just optimizing different things. Okay, before I go on, does anybody have any question about sort of where we're headed? I hope everybody had a good Easter. It was a weird Easter because I got the opportunity online to go to my friend's church in West Virginia. Didn't think I'd ever do that. I got plenty of churches around here I can go to. But that was kind of interesting. And it was a nice spring day. The spring part of this is beautiful outside, and this is a very strange juxtaposition with all the pandemic problems. Those of you who know science majors or are science majors or know anything about science, it's a study in something you'll never see again in your lifetime. So pay careful attention. I already have thought to myself, I wish I had kept a journal. I wish I was keeping a journal because I see things that I didn't see before. All kinds of things. So anyway, the way I escape that is I do math. So here we go. Okay. So let me share with you what I want to talk about today. Well, before I do that, I'm going to bring it up, but I'm going to ask you if you had any particular problems with the homework. Let's see if I can find out where this is. Right there. Okay. So I'm going to carry one of these things all the way through, but tell me if you had any particular problems with homework. Anybody? I think that probably any problems you had with the homework last time, I'm going to answer this time by things that I'm going to do because I'm kind of packing all this stuff together now in one package and kind of giving you a roadmap for how we do them. So, when you're doing your own, when you're doing your quiz, when you're doing your test, I'll hopefully have this video posted and you'll go through the process. You'll be able to look at the process I go through to find the answers to all these questions. Now, you got to do the derivatives right, but that's you should be able to do that. Haven't had a lot of practice. Okay, anybody question before I start? All right, let's look at something here. On this problem right here, I am going to take a function and I'm going to do everything we've done with it over the last several days. Okay, last week basically. First thing I want to do in order to answer the beginning questions is find the derivative of that function. And maybe even the first question is find the domain of that function. So guys, are there any values I have to kick out of that function? What's the domain of that function right there? Anybody? Turn your mic off and talk to me. Anybody? What about the domain?
All real numbers?
It's all real numbers because there are no places where we're going to get zeros in denominators here. So the domain on this thing is minus infinity to infinity. Now, what that's going to tell you, and you'll understand more about this later when I do asymptotes, but what that tells you is that it's also, for this particular function, because it's a polynomial, it's continuous everywhere. So when I draw my graph, there are not going to be gaps or holes or jumps or anything like that. That's what we learned sort of the first part of the semester. So the first derivative on this one is going to be 3x squared minus 3. Okay, just a simple power rule problem. Be careful with it. If I want to find the critical numbers, I'll set this equal to 0. So critical numbers are places where it either is equal to 0 or fails to exist, assuming the function exists there. So in this one, in order to do that, you need to factor. So in this one, to solve that equation, this is all about the algebra part. I'll just factor out a 3. I'll realize or recognize that that's a difference of 2 squares and that I want to get 0. Now, let me just point out mistakes people have been making so you don't make them again. 3 is not going to yield you anything on this thing because 3 is 3. It's never 0. Okay, if it were 3x, then I would let x be 0. The only critical numbers here are 1 and minus 1. Okay, so the critical numbers are x equal plus and minus 1. Now, the next question, let's see, critical numbers are plus or minus 1. The next question is, where is it increasing or decreasing? Here's what we learned how to do on that. We said, okay, we're going to put these critical numbers on the number line. And we're going to test in these intervals. And these are just test points, guys. They don't come up anywhere else except in the test. You could put them on your graph, but there's no reason to, because we've got the most important things here. Do not put a 0 on this. Do not put extra things on the line. Only put the critical numbers for now. So I'm going to test in the derivative, because if the derivative is positive, we know the function's increasing. If the derivative is negative, we know it's decreasing. So in this over here, that section right there, I'm going to pick 2. Okay. So when I pick 2, if I plug 2 into this, now remember again, it's the derivative I'm plugging into. If I plug 2 into that, I'll get 2 minus 1 is 1, 2 plus 1 is 3. 3 times a positive is positive. Over there, it is positive. That tells me that this thing is increasing. I'll go ahead and write it. It's increasing, positive derivative. Between minus 1 and 0, say it's 0. 0 minus 1 would be negative. 0 plus 1 would be positive. We got 3 times a negative times a positive. That is a negative. That tells me that over there on that side of 1, it is decreasing. It is also decreasing on that side where minus 1 is. Finally, if I plug in a test point over here, say minus 2, that'll be minus 2 minus 1 is negative. Minus 2 plus 1 is negative. Notice I don't care what the value is. I just care that it made these two negative. So a negative times a negative is a positive, times 3 is positive. That tells me that sorry, I drew something wrong here. I drew it totally wrong. That means it's increasing on this side. So it's increasing and decreasing. What I drew, when you draw something that's decreasing, your hand is going down. So these two arrows, if it's decreasing in that same section, they should be both going down. So next thing I do is I write it in interval notation. So increasing, you'll see where the positives are. It's minus infinity to minus 1, right in here, right in there. Union 1 to infinity. It's decreasing in between minus 1 and 1. Okay. Now, I want to see if I ask, there's one thing I didn't ask on here that I really want to ask before I leave this. And I'm going to write it and then I'll worry about it in a minute. Let me see if I've got any extra room down here. I'm going to write it down here, but I want you to notice right here, what's occurring, now talk to me, cut off your mic and talk to me. What's occurring at minus 1 if you're going up on the left and down on the right of minus 1? What's occurring there, guys?
Yeah, absolutely.
That's it's not absolute, but it is local.
Local max.
Okay, it's local. I don't really know if it's absolute yet or not, but it's local. So we're going to say, let's see if I can, I'll go down here. So what we say with that is that we have a local max, at minus 1. That's the way I want it said, minus 1. What it is f of minus 1. Now, what I do to find the y value, of course, is go all the way back to the function and put in minus 1. If you look at this one, f of minus 1 is minus 1 cubed. Minus 3 times minus 1, which is minus 1 plus 3, which is 2. Okay, so going back to where I was stating it, there's a local max at x equal minus 1. F of minus 1 is 2. Okay, you get what the max actually is by plugging where it happens into the original function. All right, let's look at this other one. Down right here at around 1, I'm going down, decreasing, and then coming up. What's happening there, guys? What's happening at 1? What's happening at 1?
Local min.
It's a local min. It's pointing to a low point. So I'm going to go and write that. So we know there's a local min at, or a local min at, I should have put at there, but anyway, at x equal 1. It is f of 1. And if you go back and plug 1 into the original function, 1 cubed is 1, minus 3 is minus 2. So right there. Now, this gives you a couple of things, guys. Number one, it gives you some points on the graph. A point on the graph right here then is minus 1, 2. And we'll plot that because we know it's a high point. This one is 1, minus 2, which is a local min. And we'll pay attention to that in a second. Okay, any question on the derivative, increasing, decreasing, local mins, local maxes? Okay. What we took up last time was concavity. Which way is it bowed? Is it bowed upward or bowed downward? The way we find concavity is we take a second derivative. Well, the first derivative was 3x squared minus 3. So the second derivative is 6x. Okay. Now, you find out where that thing would be 0. It's a lot like critical numbers. They don't call them critical numbers unless they come from the first derivative, but it's basically the same thing. That'll be 0 at, well, what value of x will make 6 times x 0? Anybody? What value do I need there?
0.
I need 0. I'm going to put 0 there. And now I'm going to test in the second derivative. If I pick a number over here, right in there, and I say it's 5, 6 times 5 is 30. That means I get a positive second derivative. What that ultimately means is when you get a positive second derivative, you have something that's concave up. If I move to the left of 0 and pick negative 5, 6 times negative 5 is minus 30. That tells me that's minus. Where the second derivative is minus, I get concave down. So I'm going to do the same thing I did with increasing, decreasing. I'm going to write it in interval notation. It's concave up from 0 to infinity. Remember, over to the right's infinity and over to the left's minus infinity. Okay. It's concave down from minus infinity to 0. Now, this is important because we defined one more thing when we were talking about second derivatives, and that was the notion of an inflection point. And guys, an inflection point is a place where concavity changes. All you need to do is find an inflection point is look at your concavity graph and see where it changes signs. That's where it changes concavity. It goes from down to up in this case. So there's an inflection point with an x coordinate of 0. Once again, you still have to find what goes with it. And if you're looking at a point on the graph, it always comes from the original function. So when I go back to the original function, if I plug in 0 here, 0 cubed minus 3 times 0, it is 0. So the inflection point is, actually it is a point, you list it as a point. That's very different from the local min and the local max. With local min and local max, you tell me what the y is and where it occurs at the x. Okay, now, here's what I'm gonna do. I'm gonna make a master line. And on that master line, I am going to put all the things that occurred on the 2 lines I did before, up above. A 0 occurred on the concavity line. A 1, let's put that up there. A 1 and a minus 1 occurred on the increasing, decreasing line. Now, unfortunately, my screen is not as big as I'd like it, but let me show. I'm gonna put everything that has happened here. Okay, let's look right here. It is decreasing between minus 1 and 1. Ignore the 0 for now. That has to do with concavity, but in between minus 1 and 1, I'm gonna write decreasing. So it's decreasing, decreasing. I already wrote that up above, so that's what I get there. It is, and it's anywhere between minus 1 and 1. it is increasing from 1 to infinity. So I'm going to write increasing right here. All right, I'm going to write increasing over here. See, it was increasing from minus infinity to minus 1 right in here, and from 1 to infinity right in here. Okay, that takes care of, I don't like where these, I don't like where my critical numbers are actually, because they're kind of getting in my way. I want to put the 1 down there. I'm going to put the 0 down there, but these are the things I put on the number line, okay? The 0, and I'm going to put the minus 1 right there, down there. Okay, so down there. Okay, so I'm going to leave. Okay, so I'm going to now put the information about concavity on it. With concavity, everywhere to the right of 0, it was concave up. So here is 0 right here. Here's 0 right here. I'm going to put concave up everywhere in every section to the right of 0. So I get concave up here, and I get concave up there. To the left of 0, in other words, from minus infinity to 0, it was concave down. So I'm going to put concave down here and concave down there. Now, guys, there are only 4 shapes I'm dealing with here. And I can draw each one of those shapes if I have that information. Increasing concave down. Now, I'm gonna draw the 4 shapes and let you pick. Suppose I'm gonna do it kind of small here. That's your 4 shapes. They're different. No, they're not different. I drew the same one over again. Hang on. Okay, let me do a little better job of that. All right. So there's a shape. Call that 1. We'll call this 2. 3. I'll call that one, and I'll call that one 4. Okay. They are all different shapes. I want to look at these 2 things and see which shape this really is. Increasing concave down. Now remember, concave down is dumps water. It's like bowed downward. So already, if we see concave down, we know it's either got to be that one or that one. It's got to be 1 or 3. Now I know that it's increasing. Which one of these is both? Both of them are concave down, but which one is increasing? When you draw it, which one's your hand going up in?
1.
1, exactly. So that's what I'm drawing right there. Okay. If you look at decreasing concave down, again, that's concave down and that's concave down. Which one is decreasing?
3.
3. Okay. So that means it's that shape. Decreasing concave up. There's going down and it's bowed upward. That's got to be that shape. So it looks like that. Increasing concave up. There's only one left here. Looks like that. It's going up. My arrow's going up as I see it, and it holds water, sort of. It's bowed upward. Okay, that's concave up. So that looks like that. Now, I'm going to tell you a couple of ways you know you got the right thing. And then tell you how to put it all together. We know that a local max occurred at -1. That's exactly what that's indicating. This way, I see a high point there. We knew there was a local min at 1. That's what's happening there. I've got the right shapes, okay? I've got it going down and then going back up. So what I want to do with all of this information is draw a rough picture of this thing. So the first thing I'm going to do is put all the points that I have on here. So I have 0, 0. That was my inflection point. I have these points I got from my local max and local min. One of them was 1 minus 2. So let's just do that one. We'll do this. So that's 1, 2, 1, 2, minus 1. So I'm going to plot my points. The other one, I forgot what it was already. -1, 2. So there's -1, 2. Remember, that was my local max. When I come down, it's 1 minus 2. That doesn't come up very clearly, but that's a minus 2, guys. 1 minus 2. 1 minus 2. Okay. So I plot that, and that's right there. 1 minus 2. Now, here's where I use my master line. I look at the shapes. To the left of -1, it's increasing and bowed downward. I have got to get to this point right here with an increasing bowed downward shape. That looks like that. Increasing bowed downward. If you go back, and ideally it's better to have the master line in front of you, but decreasing concave down is decreasing and bowed downward on the way from -1 to 0. So there's 0 right there. You want to make sure of where your points are. Decreasing concave down looks like that. Okay. The next shape was decreasing concave up. There it was right there. So on the way to this point, on the way to 1, or yeah, 1 right here, it's decreasing concave up. And then finally, it's increasing concave up. It's got to have that shape. So starting there, it goes up in a concave up form. You haven't plotted many points, but you've gotten a fairly sophisticated graph there by looking at that. Notice there, there's the max, the local max is 2. It occurs at -1. The local min is -2. It's the lowest one around there. And it occurs at 1. Okay. Now, notice I did not ask about absolute maxes or mins, because if that's all the information I give you, it keeps on going up. It keeps on increasing to the right of 1. It keeps on decreasing to the left of -1. Okay. So what happens here is this: what would trigger that absolute thing? Because there are no absolutes in this one. What would trigger that, guys, is if I, for instance, cut it off. So suppose I said, okay, I want to cut it off right here at -2.5 or something. And I want to cut this one off at, say, 3. I don't know what it looks like here exactly, guys. But if I want to cut it off, then what's going to happen here, and I don't know, that's probably going to erase everything I've got there. Yep. We would do this. If I have got a, I don't want any of this. So if I've got it cut off, then I can say what is the highest point or what is the lowest point, okay? In this case, the lowest point was, the way I've got it drawn, it looks like the lowest point would still be -2 at 1, but the highest point might be, it's higher at the end point here, so it'll be, whatever goes in there when I plug that into the function. You always get points on your graph by plugging into the original function. Question about all of that, and that's what this quiz looks like that you've got to do. It's a function, take the derivative, do all of this, get me a picture. Now, you can, and honestly, you can put this function into your calculator and you can say, yeah, I got the right shape. That's what it looks like. But I'm not going to accept this for credit unless I see all these places on it and the fact that you tested them, okay? I mean, I know you can graph this with a calculator. I'm getting ready to give you one you can't graph with a calculator, okay? But that's what it looks like. You can always check it. I mean, you got your calculator right there. Has anybody got any questions? Okay. All right. So you okay? There's a lot to do, and it'll be a fairly large portion of your next test, because it'll be the whole page, 2 pages. Do all this information and then put me the graph on the back page. So you need to be careful with this. All right. So I'm gonna give you something that maybe I don't give you the function for, and see if you really know what the calculus says. All right, suppose this one says finding a graph without a function. What happens in this problem is that I'm going to give you all the information that you need. And I'm going to tell you how the derivative's behaving. I'm going to tell you how the second derivative is behaving, and you're going to make a master line out of the information that I give you. Okay? So let's start by looking at my graph here and doing this. I'm going to ask you what color I want. I'm going to ask you what this information right here tells you. If I tell you that the function at 0 is 0 and the function when you plug in 2 is 0, what am I giving you there, guys?
Points.
I'm giving you points. Exactly. If I say plug this into the function, you get 0, I am giving you 0, 0, and I'm giving you 2, 0. Okay? So everybody good with that? F of 0 is 0 means if I plug in x equals 0, I get y equals 0, the point 0, 0. So the first thing I'm going to do on this is I got to have something to hang this graph on. So I need a few points. The other one I've got is 2, 0. So those 2 points are on there. It doesn't tell you, that doesn't tell you much about this graph. I could draw an infinite number of graphs through those 2 points, but the rest of the information is going to help me know what happens here. All right, let's look at the second piece. Let's look at this. This says f prime of x is less than 0 for x less than 1. Okay? And f prime of x is bigger than 0 for x bigger than 1. When I say something's less than 0, what kind of number is it, guys? What kind of number is it? If something's less than 0, what kind of thing is it?
Negative.
It's negative, right. So what this tells you here is the first derivative is negative for less than 0. This tells you that the first derivative is positive for, if it's less than 0 if x is less than 1, and it's positive if x is bigger than 1. And 1 is the place where it changes. Here's what they're giving you with that, guys. They're telling you that 1 is pretty important point, and to the right of 1, I get positives. And to the left of 1, I get negatives. Erase that so it doesn't confuse things. So this is the information you get from the first derivative. It changes from being negative to positive at 1. Now, what does the first derivative tell you again? What about the function does the first derivative tell you? Does it tell you concavity? What did the first derivative, let's go back to the one I just did.
Where it's increasing and decreasing?
Yeah, when I took the first derivative on this one and I put the numbers on the number line, I found out where it was increasing and decreasing. Guys, the first derivative tells you about increasing and decreasing. So you don't have a function to look at here, but they tell you where the first derivative is positive and where it's negative and where it changes. It changes around 1. What that tells me then is that it's increasing over here. It's a positive first derivative. It's decreasing over there. Okay. Now, so 1 is actually pretty important. And I probably, when they made this problem up, I don't know if I left it out or I just forgot it. They probably need to tell you something about what f of 1 is, because it's pretty clearly an important point. What kind of point is it, guys? If you look right there, if it's decreasing on the left and increasing on the right, what's happening at 1?
A local min.
Right, it's a local min. So what we say is there's a local min from all of that, there's a local min at x equal 1. And I'm going to say that f of 1 is minus 1. Let's do that. I probably should have given you that piece of information, but you need it in order to have a point to hang on to. Okay, so f of, I would have put it up here with this section of what does the f of things tell you. So I would have hung another point on there, so I would have said there's 1 minus 1. So there's 1 minus 1. Okay, now, if I look at all my information, now I only have one more piece of information. And that is this piece right here. What does the second derivative tell you about? Doesn't tell you about increasing and decreasing. What's it tell you about?
Concavity.
Concavity. This says that the second derivative is positive everywhere. It doesn't say it changes. It says it's positive. But this thing is concave up everywhere. Second derivative is always positive. It doesn't say it's positive to the right of 0 and negative to the left of 0. Then there'd be a concavity change. If it just tells you it's 0, I mean greater than 0, it's positive. So here's what my master line looks like. I'm going to do the same thing I would do normally. I'm going to draw a master line. I'm going to put these important points on them. Actually, the important point that came off the increasing, decreasing was 1. It was always concave up, but to the right of 1, it was increasing, concave up. To the left of 1, it was decreasing, concave up. Now, guys, without showing you those 4 possibilities there, decreasing, concave up, you'll know them if you do enough of them. Your pen's going down, it holds water. This one says increasing concave up. Pen goes up, holds water. Those are the 2 shapes you've got to connect for this graph. And the place where you're going to connect it is at this point 1. So right there. It's the only thing I've got where something changes. So we also said, what else is happening there, guys? We already said there was a local min there. So I think I can draw this. If it's got to go through this point, and it's got to go through that point, and that's a local max, and the shapes have to look like that and that around 1, then it's got to look like that. And then see how I did that shape? Now, you don't have to make it terribly exaggerated, guys. It's concave up. Increasing means my pen goes up and has this shape. That's what that thing looks like. There is no concavity change. It was always concave up. Look at it. It holds water everywhere. It doesn't ever turn down. Doesn't ever turn down. So my guess is that the function they were giving me all this information about was a parabola. Okay? Because that's what happens. So parabola is always concave up if it turns up. So I take the information they give me and I put it on the number line. I didn't have to take the derivatives. I didn't have to find the points. They gave them to me. They gave me all the information I needed. No inflection point here because it doesn't change. Concavity doesn't change. There's no inflection point. Okay? Question, anybody? All right, there's one other thing I want to talk to you about today. And it has to do with an application of this to business. In business, there's something called the point of diminishing returns. And we can see it easily with this problem here. It says, find the point of diminishing returns where R is the revenue in thousands of dollars and X is the amount spent on advertising. Now, let's don't worry about the function yet. If somebody wants to really push their product, they're going to do a lot of advertising to begin with. And out of that advertising, they're going to get a nice bump in revenues. You know, everybody's looking at the sign, go to this or that store, okay? And people see it and say, oh, maybe I will go by there. But after a while, you reach what is called the point of diminishing returns. In other words, your advertising has kind of gotten old and people have all seen the sign and you don't get as much revenue. It's not increasing so fast. In general, what something like this looks like, a graph might look like this, okay? Where suppose on this axis are your dollars in advertising. The dollars in advertising in thousands or whatever. And this is your dollars in revenue. notice that as you increase your advertising down here, your revenue is still going up. I mean, it's a good thing to advertise, but it's not going up as steeply. After it reaches this point, it kind of flattens out. So you've got this increase right here. But when you get to here, things start to flatten out. Now, I want to ask you something here, and I think you can see it. The graph is increasing on both sides. Your revenue is still increasing the more dollars you spend in advertising. But at some point, it's just not having the kick that it had initially. What does that point look like there, guys? What's happening on the left and the right that's changing? This is increasing. Is it concave up or concave down?
Concave up.
That's concave up. After that thing right there, it's concave down. What's this called? Where concavity changes? Yeah, it's an inflection point. That thing right there is an inflection point. So if you want to find the point of diminishing returns, you're going to find out what the inflection point is. Okay? You're going to find out what the inflection point is. So I kind of scribbled all over the next thing I was going to do, but I'm not going to do that until like whatever the next day is. What's tomorrow? Tuesday. Okay? Find the point of diminishing returns where R is the revenue, and what we've seen that it's an inflection point. So what I'm going to do on this one is take two derivatives. I'm going to find this two derivatives. R prime will be minus 12 ninths x squared. I brought the 3 down, guys, and that was the minus 12 ninths x squared plus 8x, and the derivative of 12 is 0. But it's not the first derivative I want to look at. It's the second derivative I want to look at because it's the second derivative that gives me that change in concavity. So I need to take another derivative. R double prime is equal to minus 24 ninths x, okay? And the derivative of 8x is 8, okay? Now, let me go down here a little ways.
So the diminishing return is basically just the inflection point.
Yes, so now let's find it. What I need to do is find out where concavity changes. So we do that by setting the second derivative equal to 0. So I've got minus 24 ninths. I could have reduced that, but anyway. X plus 8 equals 0. If I solve that equation, I get 8 equal 24 ninths. Guys, 3 will go into both of those, so I'm going to do that. If I move it over, it's going to be positive. It'll be 8/3. 8/3 x. Okay, I just reduced that function and moved it over to the other, that fraction, and moved it over to the other side. Now, if I divide by 8/3, that means x. That's multiplying by 3/8. If I did that on both sides by 3/8, it would give me 1x, and it would give me a 3. So if you look at 3, and put it on a line. Remember, this is the second derivative. It's going to tell me about concavity. There's the second derivative right there. If I plug in something bigger than 3, say 10 or 9, let's make it 9. It'll make it easier. The 9s would cancel. Minus 24/8 would be minus. If I make it 0, I'd get a positive 8, and I'd get positive. The concavity's changing there. The inflection point is 3, and then I'd have to plug in to the original function, to plug 3 into the original function to find what that value was there. Now, if I plug it into the original function, don't lose sight of what I'm doing here, guys. Here's what happened. When I found where this inflection point, it was at 3. And suppose this 3 right here, this axis is in thousands of dollars. That means let's spend $3,000 on advertising. And if we spend $3,000 on advertising, then it's saying that's going to be the inflection point. After that, we're not gaining as much from what we spend. What we want to know is what our revenue might be, is we'll just plug in 3 to the original, okay? And the original in this one was f of x equal minus 4/9 x cubed. Let me just find it. I know we're running out of time. Plus 4x squared plus 12. All right, plus 4x squared plus 12. If you want to finish up finding f of 3 there, you would find that point of diminishing returns. That's be 27. That's minus 3, that would be 12. Or minus 12. Plus 4 times 3 squared. Plus the 12 that was there, these 12s go. This is just plugging into 3. And I'll get 4 times 9 is 36 right there. So basically, if this is in thousands, that's your thousands of dollars of advertising. When you reach that point of diminishing returns, you have got revenues of $36,000. Guys, this one is in the book if you want to see it done a little neater. Sorry, I kind of ran out of room here. But you can look at that. You can look at that and see. But if it asks you for a point of diminishing returns, you are looking for an inflection point. And if you're looking for an inflection point, you need to look at the second derivative and where it's equal to 0. Okay, that's what I got for the day. The homework is on Moodle on the assignment sheet. If you haven't sent me your profit quiz, I need it today. Okay, I need it today. Always kind of watch your email, because usually as I get them in, I grade them so I can see how you're doing quickly, and I'll send it back to you quickly. So glance at your email every now and then. Questions, anybody? You okay? All right, that was just 2 problems, guys. Well, maybe 3. I don't know. But it takes a long time to do all of it. Email me if you have any particular questions you want to ask me. I'll try to get back in touch with you. Otherwise, I'll see you tomorrow morning at same time, same place. Okay? All right. See you later.
Thank you.
You're welcome. Bye.
Bye-bye.
Bye.